Hi and welcome back. This is Spectre P and we are Spectre AI. This is video 37, the EMBER malware with a quantum approach. This discussion starts with how classical malware detection systems actually see the problem they're trying to solve, and EMBER is a clean example because it makes that geometry explicit. Each executable is reduced to a very high-dimensional feature vector, pulling from byte histograms, opcode frequencies, section metadata, imports, entropy measures, and dozens of other engineered signals. And classification is performed by learning a boundary in that space that separates benign from malicious samples. On paper, this looks straightforward. Map samples into a feature space, learn a decision surface, and classify new inputs based on which side they fall on. The issue is not a lack of data or model complexity, but the geometry itself. As dimensionality increases, feature correlations become dense, distances lose meaning, and decision boundaries become increasingly sensitive to small perturbations in the input. EMBER exposes this problem very clearly because many malware samples differ only subtly in a handful of features while remaining nearly indistinguishable across the rest of the space. What classical models end up learning is not a stable notion of maliciousness, but an approximation of where past samples happen to cluster. This is why accuracy plateaus even as models grow deeper and more complex. Before talking about quantum methods, it's critical to understand that this is not a tooling problem or a tuning problem. It's a geometric problem rooted in how classification is framed in high-dimensional feature space, and that framing determines what any downstream method, classical or quantum, can realistically improve. As we move deeper into the feature space, the core problem becomes dimensionality itself. In datasets like EMBER, each sample lives in a space with hundreds or thousands of dimensions, and in that regime, many of the intuitions we rely on in low-dimensional geometry simply break down. Distances between points start to concentrate, meaning that the difference between near and far becomes less informative, even though the feature vectors are numerically distinct. At the same time, correlations between features grow denser, not because the data is richer, but because engineered features inevitably overlap in what they encode. This produces clusters that appear separable locally, but are globally entangled across the space. Classical decision boundaries, whether linear or kernelized, are forced to approximate this structure by smoothing over complexity, which is why we see increasingly curved and fragile boundaries as models become more expressive. The visualization here highlights a key failure mode. Small perturbations to a sample, often affecting only a few features, can push it across the boundary even though its underlying behavior has not meaningfully changed. What looks like a powerful classifier is often just a finely tuned surface stretched across a space where geometry itself has become unreliable. This is not a failure of training data or optimization, but a consequence of trying to impose classical geometric intuition onto a space where that intuition no longer holds. Understanding this breakdown is essential before introducing any quantum reframing, because it explains why simply adding more layers or more data does not fundamentally solve the problem. At this stage, it becomes clear that what we call a decision boundary in classical machine learning is not a representation of the underlying problem, but an approximation built from prior samples. The classical boundary flattens a highly structured, nonlinear feature space into something that can be expressed in Euclidean geometry, which makes optimization tractable but strips away important relationships in the data. Kernelized models attempt to compensate by introducing curvature, allowing the boundary to locally adapt to clusters and correlations, but this flexibility comes at a cost. The resulting surface is highly sensitive to the training distribution, meaning it fits what has been seen rather than what fundamentally defines malicious behavior. As new samples arrive, the boundary drifts, false positives emerge where benign behavior resembles historical malware, and false negatives appear when novel malware falls outside previously learned regions. What looks like sophistication is often just increased fragility. Both approaches, linear and kernelized, are constrained by the same assumption that classification can be solved by drawing a surface through feature space. In high-dimensional adversarial environments like malware detection, this assumption breaks down. The boundary is not discovering structure, it is interpolating memory. This distinction matters because it explains why accuracy improvements plateau and why models remain vulnerable to small, targeted changes. Before introducing any quantum formulation, it's essential to recognize that the limitation here is not computational power, but the classical framing of the decision process itself. This is the point where the framing changes completely. Up to now, everything has assumed that a sample is best understood as a fixed point in a feature space, where classification means deciding which side of a boundary that point falls on. The quantum reframing starts by discarding that assumption. Instead of treating a malware sample as a static feature vector, it is encoded as a quantum state, where the information is not just in individual coordinates, but in the relationships between them. In the classical view, features are discrete, operations are linear, and similarity is measured by distance. In the quantum view, the state itself becomes the object of interest, and relationships emerge through superposition and interference rather than explicit geometry. This does not mean adding noise or randomness. It means representing uncertainty and correlation directly in the state rather than approximating them with the surface. The important shift is that classification is no longer framed as drawing a boundary through space, but as asking how distinguishable two states are under optimal measurement. The data is not being fit to a curve. It is being prepared, evolved, and interrogated. This reframing matters because it bypasses many of the geometric pathologies we just discussed. Instead of forcing high-dimensional structure into Euclidean form, the structure is preserved implicitly in the state itself. This is the conceptual bridge between classical machine learning and quantum decision theory, and everything that follows builds on this single change in perspective. This is the point where the classical notion of a decision boundary collapses and something fundamentally different takes its place. In classical machine learning, classification is performed by fitting a surface through feature space and assigning labels based on which side a sample lands on. In the quantum framing, that surface disappears entirely. Once samples are encoded as quantum states, the problem is no longer geometric fitting, but state discrimination, determining how distinguishable two quantum states are under an optimal measurement. Instead of asking where a point lies relative to a boundary, we ask how much two states overlap, and what measurement minimizes the probability of error when distinguishing between them. This is where results like the Hellstrom bound become central, because they define the lowest achievable error rate for discriminating between two states given their overlap and prior probabilities. Nothing is trained in the classical sense. There is no curve being learned, no surface being smoothed. The system is interrogated through measurement, and the decision emerges from the structure of the states themselves. This shift is the intellectual turning point of the entire framework. Errors are no longer artifacts of misfitting a boundary. They are a consequence of fundamental indistinguishability between states. That distinction matters because it cleanly separates model limitations from data limitations and reframes classification as a problem of optimal measurement rather than approximation. Once you see classification this way, the failure modes of classical systems become obvious, and the advantages of the quantum formulation are no longer mysterious. This is not about making better guesses. It's about asking the right question of the data in the first place. Here we want to be very explicit and very disciplined, because this is where a lot of quantum work goes off the rails. What actually improves is not raw accuracy in the casual sense, and it's not some magical speedup that makes classical training obsolete. What improves is the fundamental error floor of the decision itself. When classification is reframed as state discrimination, The minimum achievable error rate is bounded by quantum measurement limits, not by how well a surface happens to fit historical data. That means greater robustness to small adversarial perturbations, fewer fragile boundary crossings, and more consistent handling of genuinely novel samples that sit near the edge of class overlap. It also means reduced sensitivity to distribution shift, because the decision is tied to distinguishability rather than geometry. What does not improve is just as important. There is no universal training shortcut, no free reduction in data requirements, and no guarantee of speedup across all workloads. The cost of inference and training still depends on how states are prepared, how measurements are implemented, and how correlations scale with the data. Quantum methods do not eliminate noise when states are fundamentally indistinguishable, and they do not remove the need for empirical validation. In other words, quantum reframing refines the nature of the problem rather than changing its computational class. This distinction is critical for trust, because it draws a hard line between principled advantage and hype. Sponsors, practitioners, and researchers can rely on this framing precisely because it says no where no should be said, and improvement only where it is structurally justified. The central takeaway from this discussion is that quantum methods do not offer a cosmetic upgrade to classical machine learning. They offer a fundamentally different way of posing the decision problem. The shift is not from shallow models to deeper ones, but from surface fitting to optimal state discrimination, where decisions emerge from measurement rather than approximation. That change immediately clarifies where the limits of performance actually live. Error is no longer an artifact of a poorly chosen boundary or insufficient model complexity. It is rooted in the intrinsic distinguishability of the underlying states. This gives us a principled way to reason about robustness, adversarial behavior, and novel samples without pretending that more data or more tuning will always fix the problem. Just as importantly, this framing is intentionally constrained. It does not promise universal speedups, free accuracy gains, or shortcuts around empirical validation. The advantages are specific, measurable, and tied directly to the structure of the data and the physics of measurement. That discipline is what makes the approach trustworthy. By being explicit about what improves and what does not, we avoid hype and focus on real, defensible progress. In practice, quantum reframing sharpens our understanding of classification limits and failure modes, which is often more valuable than incremental performance gains. The result is not a faster system but a more honest one, and in security-critical domains, that distinction matters. Thank you for watching. If you found this useful, please like the video and subscribe to the channel. It really helps us keep building deep, real-world quantum security content. You can visit spectreai.ai to explore over 55 hands-on quantum security labs and learn by doing, not just by theory. If you're interested in going deeper, you can also find our books on Amazon. And finally, leave a comment and let us know what you'd like to learn next. We read them all. Thanks again, and we'll see you in the next video.